Regularization is defined as a process that changes the resulting answer of an optimization problem in a way that makes it simpler. Simpler in this context typically means a smoother fitted resulting function or smaller norm of parameters. A distinction is made between two different high-level forms of regularization, explicit and implicit regularization. Explicit regularization directly adds in an extra penalty term to the optimization problem, whereas implicit regularization is any other method of making the solution simpler without the addition of a penalty term. In this video, we will only discuss explicit regularization. Remember that the following expression is derived from maximum a posteriori estimation in the supervised learning scenario. The first term is task-specific in that we use it to learn to predict labels given input data and the parameters using our specific dataset. We haven't discussed the second term yet, but recall it contains the prior probability of parameters, which is the probability of their values before observing the data in our dataset. How can we use this term, and what might we believe about our parameters before even seeing the data? We could assume nothing and say that all possible theta are equally probable before seeing the data. This is a perfectly reasonable assumption to make, and it is typically the first thing we try when fitting a model. In such a scenario, we would assume a uniform distribution over theta, and the second term would vanish from the problem completely, since it would be constant with respect to theta. Instead, we may believe that the correct parameters are reasonably close to zero rather than very large or small values. It's typical to assume that each individual parameter is independently drawn from either a Laplace or normal distribution with zero mean and some constant fixed scale or variance, respectively. For now, let's look only at the log prior of theta term. First, we will use the independence of parameters in the prior to write it as a product of probabilities of each theta sub j. For this derivation, we will take theta sub j to be drawn from a normal distribution with constant standard deviation sigma. We also use a property of logs that the log of a product is equal to the sum of log of the individual terms in the product to rewrite the expression as shown. Using that same property, we can further split the contents of each log into two terms. The first term is constant with respect to theta, so we can drop it from optimization over theta. Now, log and exponentiation cancel, and we can move the constants in our expression to the front. You will typically see the maximization problem be converted into the equivalent minimization problem. Picking some constant variance sigma squared is the same as picking some constant coefficient lambda. Note that picking large lambda is equivalent to picking small sigma and vice versa, since lambda is equal to 1 over 2 sigma squared. So if we upweight the importance of this regularization term by setting a very large lambda, it's the same as assuming a small variance of parameters in the prior, which will push the solution to smaller parameter values compared to if we had picked smaller lambda values. This term is known as L2 regularization. This name refers to the relationship of this term to the L2 norm. If we view theta as a vector with entries theta sub j, this term is the squared L2 norm of that vector times some lambda. Using a Laplace prior over parameters instead of a normal distribution prior, we would have arrived at the following term instead. This is referred to as L1 regularization, and the term can be recognized as the L1 norm of theta times some lambda. What effect do these types of regularization have on the result? As you can see from the PDFs on the Laplace and normal distribution centered at 0, they both have maximums at 0, so maximizing only with the log prior would result in entirely zero vectors. We can also look at the exact regularization terms that will be minimized. On the left, you can see the plot of the absolute value of theta sub j over possible values and the derivative, rate of change, of this function on the right. The derivative here is constant, approaching 0 from both sides. Comparing the plot on the left to the plot of theta squared, which we saw in the L2 loss, it's clear that we are penalized more for having many large parameter values under L2 loss. On the right, the derivative plot shows that we see a larger rate of change in theta squared when moving parameters with large values and smaller rate of change for small values. In other words, under L2, there is not a big reduction in the overall value near 0. Moving a parameter with a value close to 0 even closer has less of an effect on minimizing the term than moving a large parameter the same amount closer to 0, whereas L1 doesn't treat large or small values differently. This results in solutions using L1 loss to be more sparse, or having more zeroed out parameters than with L2. Solutions using L2 may have less large values, but more smaller parameters near 2, but not quite 0. Let's now look at the overall optimization problem. We will be using MSE loss as derived in an earlier video for the first term. We will also use L2 regularization here. Note that we do not necessarily assume the same variance on the prior parameters as we do for the noise around our model predictions. To show this, we use subscripts on the sigmas here, showing that sigma sub 1 is not sigma sub 2. We could stop here and pick values for sigma 1 and sigma 2 and try to find optimal theta. But instead of stopping here, we can also use a trick to reduce the number of constants we need to choose down from 2 to 1. First, we can reform our coefficients as constants lambda 1 and lambda 2. Multiplying the problem by a constant doesn't change the result, so let's multiply by 1 over lambda 1 to get rid of the coefficient on the first term. Let's also rename lambda 2 over lambda 1 to a different constant, which we'll denote as just lambda without a subscript. This final expression may be recognized by people familiar with regularized regression models. So over the last few videos, we have shown exactly how to derive this, starting all the way from maximum a posteriori estimation and listing the assumptions made along the way. We have not yet answered the question of what to do with lambda. Surely we don't know which exact value it should take. If you thought this, you'd be right. In most cases, we don't know the value to assign beforehand. Instead, we treat it as a hyperparameter. A hyperparameter is any value we can tune outside of the normal model fitting or optimization procedure. So for each training run, you would pick a value for any of your hyperparameters, run training, and see how well the resulting model performs. It's clearly not a parameter that is being tuned during the training itself, but we still want to find the values that are best. So there's a meta problem of finding the best hyperparameters for model training. I won't go into too much detail on different methods for tuning the hyperparameters now.